Theorem 34. Alright, so this one's going to have some kind of new terms and be a little bit weird at the start, but you'll see it's pretty, pretty quick and almost obvious proposition. So anyways, in any parallelogram, the complements of any parallelogram about the diagonal are equal. Now what the heck is a complement? Easiest way is just to kind of turn to a picture. So we see given, we have this parallelogram ABCD, and we have a diagonal AC. Pick any point on AC, we'll call that K. I'm just going to pick, say, this point. I'm going to call that point K. Through point K, I'm going to draw EKF parallel to AD. It's not very helpful. Anyways, but all three of these are going to be parallel. I'm also going to draw HKG parallel to AB. That's not very good either. But you get the idea. Alright, cool. Let's label these points. So this is alright, cool. So you'll notice that after drawing those two pink lines, this parallelogram up here at the top, AEKH, AK is part of the diagonal AC, and it's also a diagonal for this little miniature parallelogram. Likewise, KC is the diagonal of this little mini parallelogram as well. And anyways, that's kind of one of the first observations to make, that AC is now the diagonal of these two smaller parallelograms. So a complement refers to these two parallelograms here. Now, as kind of a easier way to refer to certain parallelograms, rather than naming all four corners, in a certain direction, kind of a shorter way to do that is to name two opposite corners of a parallelogram. So in this case, we're talking about parallelogram EBGK. We can just refer to it as parallelogram EG. As long as I know I'm talking about a parallelogram and I name those two opposite corners, there's no confusion that can occur. Likewise, we're going to look at parallelogram HF, and ultimately we want to show that those two complementary parallelograms are going to be equal, right? So they're called complements because they kind of finish the picture on either side of the diagonal. They're both parallelograms, we can kind of see that, and they're not oriented the same way, so it's not immediately obvious that they're equal, but as we're going to see, they are, in fact, equal. So to make things easy, I'm going to just number the several areas that we've created so we can refer to them a little bit easier. Though two we're going to be focusing on, I'm going to name them 1 and 2. And then we can go ahead and call these 3, 4, 5, and 6. Alright, cool. So, if we take a look at areas 5 and 6, we know that area 5 is going to be equal to area 6 for the reason that we said before, that AK is going to be the diagonal of that little smaller parallelogram. Likewise, 3 is going to be equal to 4 for the same reason, right? They are both halves of this parallelogram. KC is the diagonal of that parallelogram. And since AC is the diagonal of the big parallelogram, we know that everything on this side of the parallelogram or this side of AC is going to be equal to everything on this side of AC. But we can talk about that in terms of the areas. So we can say, so everything that's below AC, well, that's area 1 plus area 3 plus area 5. It's going to be equal to everything on the top of AC, which is area 2 plus area 4 plus area 6. Alright. Now, from here, since we know 3 and 4 are equal and 5 and 6 are equal, we can subtract equals from equals. So we can subtract 3 and 5 and 4 and 6, and then we end up with area 1 being equal to area 2. Area 1 is parallelogram EG, and area 2 is parallelogram HF, which is what we set out to do. So we're done. That's it. Now again, that might seem pretty obvious, but this does kind of lead to a lot of really interesting things. We could have started with those parallelograms and then set them up, have their corners touch, and then kind of recreate the giant parallelogram AC. There's a lot of really interesting things that kind of follow from this. We don't have time to go into all of them. Anyways, but it's worth kind of noticing that when I draw a diagonal in a parallelogram and it cuts things into equal parts, those equal parts have equal parts within them, and those equal parts kind of continue to be equal all the way down. For theorem 35, it's going to be pretty simple. It's just how to make a square. We're going to start with a given line segment, AB, and on AB we're going to construct a square. So just as a refresher, remember a square is a four-sided figure or quadrilateral where all the angles are right angles and all the sides are equal. So let's get to it. So the first thing we're going to do is from point A, we're going to erect a perpendicular line. And if you recall, we know that's something that we can do. We've done it in the past of on a line erecting a perpendicular at any given point. And I'm just going to erect a perpendicular line. I'm not even going to write out the steps because this theorem is pretty facile. All right, and then kind of using a circle, we can cut off an equal portion on that line. So, I mean, I'm not going to actually draw the circle, but you kind of get the idea that if I were to make a circle with center A and radius AB, I could define point C, right? That way I know that AC is equal to AB, all right? Then from point C, I can draw, through point C, I can draw a line that is going to be parallel to AB. Again, this is something that we've shown that we can do before. So I'm going to go ahead and draw a line AC parallel to AB. And then through point B, I'm going to draw a line that is parallel to AC. All right, cool. Now I claim that this is in fact a square. When I drew, let's call this point D over here to make things easier. When I drew CD parallel to AB, that means that AC is essentially a transversal cutting those parallel lines, which means that same side interior angles are going to be supplementary. Since this is already a right angle, then this angle plus this angle is going to equal 2 right angles, which means it too must be a right angle. Likewise, or by the same logic, this must be a right angle. And anyways, we could do similar logic to conclude that that is also going to be a right angle. And since we made AC and AB equal to each other, again, we can see pretty easily that we're cutting off equal portions. And so CD is going to be equal to AC. Likewise, BD is going to be equal to CD, AC, AB. Therefore, we have constructed a square, ABCD, well, actually ABDC, whatever, and all the sides are equal, and all the angles are right angles. Again, just leaning on what we already know, making perpendicular lines and making parallel lines, pretty easy to construct a square. And that's it. This is it. Theorem 36. This is the climax of first semester. Everything we've done has led us to this point, to see the truth of this demonstration. Now maybe you have heard of the conclusion of this theorem. You might know it by a different name. It's also called the Pythagorean theorem. But I doubt many of you have seen why it's true. And again, you might know that it's true, but knowing why it's true is way better. So, theorem 36. In any right triangle, the square on the hypotenuse, and again, just a refresher on vocabulary, the hypotenuse is the longest side of the right triangle. Another way to think about it, since we know that there's that special relationship between angles and the sides that they subtend or that they're across from, it means it's the side that's across from the right angle. So in our picture here, triangle ABC, the right angle's at point A, which means BC is the longest of the three sides. So BC, we would say, is the hypotenuse. Anyways, the square on the hypotenuse is equal exactly to the sum of the two squares, don't mind the typo, is equal to the sum of the two squares on the other two legs. So what does that mean? If we take a look at our picture, we have our right triangle, and you'll see this pink square is the square on AB, right? So all four of these sides are equal, and this is a square on AB. It's another way to think about it. It's AB squared. And maybe you remember talking about, like if this is x times x is equal to x squared. But what that really means is that's a geometric statement, right? What you're saying is, given some length x, and multiplication means make rectangles or make square. Make rectangles. Yeah. That means, x times x, and this is x squared. You are constructing an area when you multiply numbers. You might make a line longer with addition or shorter with subtraction, but when you multiply numbers, what you're really doing is creating areas when you think about the geometric interpretation of arithmetic. All right, so the pink square is AB squared, right? And then the blue square is AC squared, right? And again, I have it kind of written in the normal shorthand that we might be used to. And then the orange square is BC squared. What we want to prove is that BG, or the pink square, plus AK, which is the blue square, is equal exactly to BE, which is the orange square. All right, so that's a big to-do. Let's get started. Step 1, from point A, drop a line perpendicular to DE. And we'll just call that point down there L. All right, cool. Now note, maybe this goes without saying, but just notice that AL is perpendicular to DE, but it's also going to be parallel to BD and parallel to CE, right? Because in a square, these angles are all right angles, and all opposite sides are going to be parallel to each other. Anyways, we're also going to join a line from point F to point C. Ugh, that got a little ugly at the end there. Then we're also going to join the line A from A to D. From point A. Ooh, it's not very straight. Any of our pictures this year should be pretty. Should be this one. All right, cool. All right. All right, let's make a few other kind of general observations before we kind of get into the heart of this proof. So we know that the angle BAC is a right angle because we made it that way. It's a right triangle. We also know that BAG is a right angle because it's a square, which means this angle and this angle are both right angles. In other words, we have two right angles that are adjacent to each other. And then if we go back to Theorem 12, we'll remember that if there are two angles that are adjacent, that are both right angles, then they must lie on the straight line. So in other words, since these two angles are right angles, CAG must be one continuous straight line. All right. Now maybe that's obvious just from looking at the picture, but it is something that does need to be said. Likewise, this angle here and this angle here are both right angles, which means that BAH is also going to be one straight line. All right, enough on that. So now if we kind of take a look at our picture here, you know what? I'm going to redraw CF because that's just ugly. So we have CF and AD were the two additional lines that we drew after we dropped that perpendicular AL. Okay, so now let's take a look at what we're looking at here. So since the pink square is in fact a square, all the sides are going to be equal, which means that BF is equal to BA. All right, that goes without saying. Likewise, down in the orange square, we can say that BC, right, this top part, is going to be equal to BD. All right, easy enough. Excuse me. Now take a look at angle FBC. FBC. So this angle here. I'm not going to draw a little arc, otherwise this picture is going to get too cluttered. But just notice that it's made up of this right angle, right, and this angle BAC, right? Now take a look at the angle ABD. It's made up of that angle ABC again and CBD, which is also a right angle. Since all right angles are equal to each other, we can conclude that FBC is equal to angle ABD. Again, because angle FBC is made up of a right angle and this angle ABC, and then angle ABD is made up of a right angle and the angle ABC. Hopefully that makes sense. Maybe just for now, I'm going to just draw in little arcs and then erase them. So in other words, this angle is equal to this angle, right? FBC, this arc here, is equal to ABD. So you can see the two angles that I'm looking at kind of overlap each other. All right, I'm just going to erase it the best I can so the picture doesn't get too ugly. All right. So now in your mind's eye, pull out two triangles, triangle FBC and triangle ABD. And notice that we have a side on both of them, right? FB and AB are equal to each other. We have a second side, BC and BD equal to each other. And the angle in between those two sides, right? We have FB and BC and this angle, which is angle FBC. Likewise, AB and BD, the angle between them, ABD, is equal, which means we can conclude that triangle, FBC is equal to triangle ABD. Cool. Easy enough. All right. Okay, that's probably the hardest part to see because there's a lot of parts that are overlapping and stuff. The rest of it is going to flow pretty easily. So now take a look at one, excuse me, at one of those triangles. Let's take a look at triangle FBC, right? FBC. Notice that it stands on FB, right? If we take a look at, just that the triangle standing on this side. And then notice that the pink square itself is also standing on that side. And another way we can think about this is this triangle and this square are standing on the same base and are between the same parallels, right? FB and GAC are both parallel to each other, right? They have to be, which means that the triangle and the square are both on the same base and within the same parallels. And we've already established that, parallelograms on the same base between the same parallels are equal. Likewise with triangles. And we also notice that the relationship between triangles and parallelograms, a triangle and a parallelogram on the same base between the same parallels, the triangle will be exactly half the parallelogram. Now in this case it's a square, but that doesn't matter. But what this means is that triangle FBC is exactly half the pink square. So another way we can think about it is 2 times triangle FBC is equal to the square BG. Likewise, we can take a look at triangle ABD and parallelogram BL, or rectangle BL. This means that since they're both on the same base and between the same parallels, we can say 2 times triangle ABD is equal to the parallelogram BL. Cool. That's convenient. All right. Now comes to we come to the kind of the last portion. It's going to be very similar to what we did here, so we're going to kind of go through it quickly. But essentially what we've proven is that the pink square and this rectangle BL, right, this part down here, are going to be equal. Sorry, I forgot to write that. Done. From here we can conclude that the pink square, that is BG, is equal exactly to the parallelogram, or the rectangle really, BL. Alright, phase 1 is done. Now for phase 2, we're going to draw 2 more lines, and the picture is going to get a little bit cluttered, but that's okay. We're going to draw a line from point A down to the corner E. After we draw AE, we're going to draw another line from K to B. All right. Now, again, we're not going to walk through all the logic again. I kind of wrote out the steps pretty easily. But if we take a look at triangle BCK and triangle AEC, we can see that those 2 triangles are also going to be equal for the same reason that we gave before, right? We're going to have side, angle, side, side, angle, side, and therefore those 2 triangles are going to be equal, right? And that's what we have here. And each of those triangles is going to be half of some parallelogram on the same base within the same parallels. So triangle BCK is going to be equal to half of the blue square AK. Likewise, AEC is going to be equal to exactly half of this rectangle CL, right? Right? That's what this is. So twice those triangles is equal to the whole parallelogram. Therefore, we can conclude that the blue square is equal exactly to this rectangle down here, the rectangle CL, right? This guy right here. Okay. At this point, we're going to take, let's get a different color here. If we take what we got down here and we take what we got up here, we can conclude uh, you know, since the square BG is equal to the rectangle BL, and the square AK is equal to the rectangle CL, we can add those together and say the square BG plus the square AK is equal to BL plus CL. So BL plus CL. But we see that the sum of those is equal exactly to the square BE. And this is what we wanted to prove. The square on the hypotenuse, BE, is equal exactly to the sum of the squares on the two sides, BG and AK. The pink square plus the blue square equals the orange square. And that's it for the demonstration. I'm going to show some other kind of ways to kind of see the truth of this, as well as like just a few quick examples of kind of the implications of this truth. So up here at the top might be what some of you have maybe seen before. If we have a right triangle and we call the sides A, B, and the hypotenuse C, then the way to kind of write this truth kind of universally is that A squared plus B squared is equal to C squared. And again, this is called the Pythagorean theorem. So this is a really beautiful truth, and it's extremely helpful when trying to untangle certain problems in mathematics, because if you can find a right triangle somewhere in your picture, then you know a lot. For right triangles, the sides lengths have this special relationship, which can be really helpful for solving triangles and other such things. All of trigonometry is kind of based on this principle that if we can reduce our picture to right triangles, then we can figure out pretty much anything we want. And that's obviously helpful. So just, as a quick example of kind of what you might see on your homework, if we take a look at this first example, if we have this right triangle, the hypotenuse is unknown, but we know that one side length is 3, one side length is 4, then we can solve for C pretty easily. Just acknowledge that, this unknown is in fact the hypotenuse, and that's always going to be, the one that's all by itself, which makes this A and this B, or, vice versa, doesn't matter. So what this means is that 3 squared plus 4 squared is going to be equal to C squared. Now 3 squared is 9, 4 squared is 16, is equal to C squared. 16 plus 9, that's going to be 25. Now at this point, we could square root both sides to determine what C must be, or we can just ask the simple question of what number times itself is equal to 25 exactly. And you can probably see pretty quickly that C is equal to 5. The third length of this triangle is 5. That's pretty helpful. But again, if you don't know that off the top of your head, you can use the square root function on your calculator. Now let's take a look at this one over here. In this case, 13 is the hypotenuse, right? So that's going to be the C squared. And A is the unknown. So we can set up an equation for this. We can say A squared plus 12 squared is equal to 13 squared. Well, I know that 12 squared is going to be 144, and 13 squared is going to be 169. Subtract 144 from both sides, and we get 25. Oh, looky here. This looks familiar. Square root both sides. We find that A is equal to 5. Again, now obviously I can try these examples very particularly, and it's not always going to be neat numbers. But the point is that this is one application of using this formula that you're probably going to see on your homework. But the beauty of this truth has much greater implications. Anyway, just a couple quick examples of how you can set up a problem to find the unknown side of a triangle. All right, this is just one more kind of visual proof. It's not a proof in and of itself, but it is kind of a way to look at what we've kind of just learned to be true in a different way and see that it actually does hold water. So what I've done is drawn two identical black squares, and you'll notice that the side of both of these squares is a plus b. So for each square, it's going to be a plus b, quantity squared. So the side length of both of those squares is a plus b. Now if we take a look at the square on the left, you'll notice that by drawing those two bold lines, I get this little square up here, the bigger square, and then these two rectangles that I've kind of cut in half. So since for this little square, you can see that both sides of it are a, which means that this little square is equal to a squared. Likewise, this big square, it's b on both sides, so this big square is b squared. And then with the two remaining rectangles, which now we would call them complements, we know that they're going to be equal. But for the sake of the demonstration that's to come, I drew diagonals, and we can see that every one of these four triangles is a copy of the basic triangle that I'm dealing with. I'm just going to number them 1, 2, 3, and 4. All right. Now if we look over to the right-hand side, again, this is an equal square with side length AB, so it's AB squared. And notice that we have these little triangles again, right? With this is a right angle, so AB, which means that this long side must be C. Likewise, this must be C, C, C. Which means that this little square that's kind of tilted inside must be C times C, or C squared. And then we also have 4 copies of this triangle, so 1, 2, 3, 4. And now we can kind of see the truth of the Pythagorean theorem in kind of a different way. These two squares I made identical. They started off equal. And both squares are equal exactly to 4 of these little triangles and then some squares. So on the left-hand side, we have a squared plus b squared plus 4 triangles. And on the right-hand side, we have c squared plus 4 triangles. Right? Let's go ahead and write that out. On the left side, we have a squared plus b squared plus 4 identical triangles. On the right-hand side, we have c squared plus 4 triangles. I can subtract the 4 triangles from both sides, and we end up with a squared plus b squared is equal to c squared, which is in fact